In this video, we're beginning a discussion about the derivative of a vector function. We're going to consider a vector function, r at t, in two-dimensional space, just to make it easy to draw. And let's consider this r at t vector function as being a vector function that traces out some curve c. And when we have a vector function that traces out that curve, what we do is plug in values for the parameter. So we'll plug in t is equal to, let's say, 0. The output is a corresponding vector that we call r at 0. The terminal point of that vector is going to be a point on the curve. We plug in a different value for the parameter, let's say t is equal to 1. We plug that into the vector function. We get another vector, we'll call this r evaluated at 1, that terminates at a point that is on the curve c. And we keep doing this. R evaluated at 2 is going to terminate at another point that's on our curve until we trace out the entire curve c. Now, when we talk about the derivative of that vector function, it's an exciting reality that in order to determine the derivative of a vector function, all we need to do is differentiate the individual components. So if we have a vector function with f at t and g and t as the components of that vector function, f prime at t and g prime at t are going to be the components of the derivative function. Now, this derivative vector function is going to yield a vector that is pointing in the direction of the tangent line to the curve c at a particular time. So let's try to understand that back up here at the general case. So at time is equal to t, let's say that we're arbitrarily choosing some value of t. We get a vector as an output that's pointing to a specific point on the curve. If we then determine the derivative vector function, that derivative vector function is going to yield a vector that if we had it initiating at the terminal point of the position vector, that vector, the derivative vector, would be pointing in the direction of the tangent line. So just like within Calc 1, when we take the derivative of a scalar function, we get the slope of a line that is tangent to the curve. When we take the derivative of a vector function, we get a vector that is pointing in the direction of the line that is tangent to the curve. So there are a lot of similarities with what we're doing now to what we saw back in Calc 1. And this situation does also apply to vectors in three-dimensional space. If we have a vector function that's tracing out a space curve in three-dimensional space, in order to determine the derivative vector function, all we need to do is to differentiate each of the individual components. And again, that derivative function is going to be pointing in the direction of a line that is tangent to the curve at a particular time.